Swayam Prabha. Digital India. Educated India.
Welcome to the course on micromachining sponsored by DTH. Today I am going to discuss about the anode shape prediction and tool design for electrochemical machining and electrochemical micromachining. Organization of the talk is as follows: Introduction to tooling design for ECM and ECMM, anode shape prediction in ECM and ECMM, other approaches for anode shape prediction in ECM and ECMM, what is correction factor method of tool design in ECMM, finite element method for the anode shape prediction and tool design in ECM and ECMM. Now, it is assumed that you have already studied the lectures on electrochemical micromachining. Then I will talk about the conclusions, and some references are given at the end of the talk. These are some of the references given or referred in this particular talk. One is the anode shape prediction and tool design for ECM processes in Advanced Machining Processes book. This is very important. MS Reddy and others. Tool design for ECM, correction factor method. I am going to discuss about it in detail in one of the lectures. And then there is another paper, anode shape prediction in through mass electrochemical micromachining using finite element method. And finally, there is Vijay Bhattacharya's International Journal of Machine Tools and Manufacture paper published over there. I am going to discuss part 1. This will take 2 lectures to complete this particular topic. Introduction to tooling design in ECM and ECMM. ECM and ECMM capabilities. ECM and ECMM, they are controlled anodic dissolution processes having very wide applications. Potentials of this process have not been fully exploited due to the following: complex nature of the process, anode or workpiece shape prediction problems, and very importantly, tool or cathode shape prediction or tool design problems. This lecture deals with second and third problems of ECM and ECMM. Important note: there are various methods for anode shape prediction and tool design evolved by different researchers for ECM, which are applicable for ECMM also, with minor changes, minor modifications. Working principle remains the same for both the processes. Methods of anode shape prediction and tool design in ECM: cos theta method, conducting paper analog method, very old method. Para Production Engineering Research Association proposed a method: empirical approach, nomographic approach, complex variables approach, finite difference method, finite element method. Now, these are the different methods which are applicable for ECM and with certain minor modifications. They are also applicable for electrochemical micromachining, that is why I am discussing them over here. And finally, boundary element method. There are other methods also, all of them cannot be discussed here in a short period, but some of them I will discuss them in detail in the following lecture. Tool or cathode design problems. Now, for tool designing, again some of these methods which I have just mentioned for anode shape production, they are applicable for it. Cos theta method, complex variables approach, finite difference method, finite element method, boundary element method, and finally correction factor method. I will give enough importance on this particular topic in the second lecture, because this is the method evolved basically for tool design purposes. Tooling design in ECM. Tooling design problems include anode shape problems as well as tool design problems. Anode shape prediction analysis problem can be solved. The analysis problem deals with the prediction of work profile or workpiece profile obtainable from a given tool while operating under the specified machining conditions. Cathode shape prediction is a tool design problem. The design problem deals with the computation of the tool shape and size, which under specified machining conditions would produce a workpiece having the prescribed shape and size, accuracy and surface finish. So, to obtain the desired workpiece, you need to have tool design first, then optimization of the machining condition, then only perform the machining operation. Otherwise, you may not get the desired accuracy, tolerances, surface finish on the machined workpiece. Note: anode shape prediction and tool design procedures are different for different kinds of operations, say plain parallel machining, drilling, milling, turning, etc. For example, I will discuss mainly plain parallel electrodes machining and little bit details about drilling operation, that is electrochemical micro drilling. In this lecture, main emphasis is on the principle, not different kinds of operations. Means it will be mentioned basically how to proceed for anode shape prediction and tool design for a specific type of process. Material removal in ECM and ECMM. We all know this particular figure, that wherever there is a smaller gap between the tool and workpiece or the smaller inter-electrode gap, higher current density will be there, and wherever there is a larger gap, smaller current density will be there, and material removal takes place according to the current density. Higher the current density, higher is the material removal rate, lower the current density, lower is the material removal rate. Now, you can see if you machine this workpiece with this tool for the specified machining condition, you will get this type of the shape of the workpiece. You can see this is the tool, and once you machine this workpiece, you get approximately inverse replica of the tool on the workpiece. That is what you can see here as well as here. Now, I am deliberately telling the word approximately, because unless you have accurate tool design, you cannot get exactly what you want. Production of approximate inverse replica of the tool on the workpiece is done at the initial stage. You can see here, this is the approximate replica of this particular inverse replica of this particular tool over here reproduced. Three types of the tools: You must have seen it while dealing with the electrochemical micromachining. Anode profile obtainable from the bare tool. You can see here, this is the bare tool, no coating, no bit is there, and this is the kind of the anode shape you are going to get. This is the electrolyte coming through the tool and going out from the sides, and bare tool gives a tapered side wall. These are the tapered side walls, and here is the coated tool. That means if you coat the sides of the tool, then no current will flow because it is non-conducting. So, no current will flow from here to the workpiece and no machining will take place, and you can see the effect. This side of the drilled hole is more or less a straight side. So, that means here inter-electrode gap is more or less constant. So, this is the difference if you are using the coated tool. Now, here is the bit type of the tool. Note it carefully, here whole tool is made up of metallic material, which is costly and difficult to make it. Here if you see, here only this part, that is the bit, is made of metallic material, rest of the part is the tool holder or bit holder made of perspex and electrically non-conducting material. So, material will be removed from the sides against this wall and from this front gap over here. Here is the hole. So, electrolyte is coming in and going out from the sides. So, see it carefully, here the shape of the drilled hole is better even with the coated tool, slightly or same as the coating tool, and you can see here it is almost straight while it is almost tapered, fully tapered where you are using the bare tool. So, insulation of the tool, bit type of the tool is a better solution, as you can see here, or this insulation over there. These are the different parts. Accuracy and surface finish of tool affect workpiece accuracy and surface finish, especially in micromachining zone. Now, most of those parts I have told you. So, this is the transition zone, this is the front zone, this is the this is the what is this, 7 is the transition zone and 5 is the stagnation zone. I am sorry, this is the stagnation zone, this is the transition zone, and this is the side zone over there. Parametric difference between ECM and ECMM. You can see the values of the different parameters used in ECM and ECMM. This is important to understand, because ECM you are dealing with macro and meso size components and features. In ECMM you are dealing with micro size features. So, you can see current value in ECM is 150 to 1000 ampere, while it is ECMM less than 1 ampere. Power supply may be continuous or pulse in ECM, but in ECMM mostly it is the pulse power supply. Voltage used in ECM can be as high as up to 30 volt in special cases, but in case of ECMM it is 1 to 5 volt. Electrolyte concentration normally greater than 20 gram per liter, while in ECMM it is less than 20 gram per liter. Size of the tool is large to medium in case of ECM, depending upon the feature required on the component, but here it is normally of micron size. And inter-electrode gap can be as high as 100 to 600 micrometer, but in case of ECMM it is 5 to 50 micrometer only. Here you can perform the maskless operations in case of ECM, but in ECMM both are possible, maskless as well as with mask. Surface finish is good in case of ECM 0.1 to 0.15 micron, but in ECMM it is still better, 0.05 to 0.04 micrometer. These are the numbers which are obtained normally, but not necessarily that they cannot go down or they cannot go up. All this will depend upon what machining conditions you are using during machining. And electrolyte flow velocity 10 to 60 meter per second in case of ECM, while it is less than 5 meter per second in case of ECMM. And reason is very simple. I have explained in other lectures that electrodes are very small in size, and if You have the large force of the electrolyte on the electrode, it may damage, it may bend, and then the feature created will not be accurate. Introduction to anode shape prediction in ECM and ECMM. What is anode shape prediction in ECM and ECMM? Consider the case of electrochemical machining of plain parallel electrode. For understanding the process of anode shape prediction, you are given following inputs: machining conditions, which includes voltage, inter-electrode gap, electrolyte conductivity, electrolyte flow pressure or electrolyte flow velocity, electrochemical equivalent of anode material, that is workpiece material, and tool profile, xy coordinates or xyz coordinates of the tool. Now, using a particular method, finite element method, finite difference method, empirical method, etc., calculate the inter-electrode gap at different points along the tool axis. Finally, the inter-electrode gap is calculated and for different points on the workpiece. Now, finally, these points should be joined to get the obtainable anode profile, and once you get these different points or nodes on the workpiece surface, you join them and then you will get the final simulated or computed anode profile. Now, feed rate. Now, there can be two cases, one feed rate is 0, in another case feed rate is finite. Example of plain parallel ECM plus ECMM for 0 feed rate, anode shape prediction for f is equal to 0, that is finite feed rate is 0. Now, this is the tool, this is the workpiece, this is the discretization of the inter-electrode gap in different elements like 1, 2, 3, 4, 5. These are the triangular elements. U is the velocity of the electrolyte going in, T0 is the temperature of the electrolyte. This is the inter-electrode gap, that is the gap between the tool and the workpiece. At 0 second, it is the status of the tool and workpiece. You can see here tool shape given is plane over here, initial workpiece shape is plane over here, and these are the triangular elements with 3 nodes at nodes each. Now, you can see here this is one element, 1 node, 2 node, 3 node. So, each element has 3 nodes. Now, after some time 50 seconds, when you keep machining it for 50 seconds, you will see that material is removed from the workpiece and it becomes tapered. Here at inlet, temperature is T0, velocity is u, here material removal is minimum. Now, as electrolyte moves forward, the temperature of the electrolyte keeps on increasing, and once the temperature increases, electrical conductivity increases, and if conductivity increases, material removal rate will increase. So, you can see here this becomes tapered and larger material is removed at the exit as compared to the inlet. However, one should not forget that sludge is also being formed in electrochemical micromachining, and that sludge may reduce the electrolyte's electrical conductivity, while temperature increases the electrolyte's electrical conductivity. Bubbles are also formed, hydrogen and oxygen gas bubbles, they contribute to the reduction of the electrolyte's electrical conductivity. So, it is really a combination of all these three, and whether it increases or decreases will depend upon their percentage and their effect on the electrical conductivity. So, you can see here after 100 seconds this has become quite small over here. So, sufficient material has been removed from this end and minimal material is removed for this point. Now, this is looking straight, but in real life it may not be so straight, because conductivity it will be decided by the current density, which will depend upon the conductivity of the electrolyte along the flow path. Anode workpiece shape produced after 100 seconds. So, this is the workpiece shape, and theoretically you have to calculate this particular shape after machining for 100 seconds. So, as mentioned earlier, you do the things at the nodes of the elements. This is the one node, this is the another element, another node of the element. This is the one node, this is the another node of the element. And note it, the size of these elements is very, very small. It may be less than 1 millimeter side of these elements, depending upon how much accurate you want the prediction. Material removed in 100 seconds at different locations is shown over here. Anode shape prediction for F means feed rate is not 0 during ECM and ECMM both. Now, this is the same as we have already discussed. Here feed rate is F1, that means tool is moving with F1 feed rate towards the workpiece. So, what does it mean? When tool is moving towards the workpiece, with time the inter-electrode gap will not keep on increasing continuously, rather it will keep on maintaining a certain inter-electrode gap, depends upon the machining conditions and the feed rate. So, you can see here U and T0 are the same as in the earlier case, that is at the beginning. Now, U and T0 remain the same, but this is the inter-electrode gap. This is the inter-electrode gap here, this is the inter-electrode gap here, and this is the workpiece shape after 50 seconds. And if you see here, this is the kind of the material that has been removed. This is at this particular point and this is at this particular point. So, maximum material is removed from the end, at the end or by 3 point, and minimum is removed from by 1 point over here. And tool feed is F1 millimeter per second. So, you can see here it makes a difference in the final shape of the tool, whether you have 0 feed rate or you have finite feed rate. This is the shape I have mentioned to you. Anode profile after electrochemical drilling and electrochemical micro drilling with bare tool. Now, this is coated tool, this is coated, not bare tool, this is with coated tool, sorry. This is with coated tool, and you can see here it is reasonably straight sided, here it is partially coated, this is bare tool, this is bare. So, it is partially coated, electrolyte is coming out from here, going out from here, and you can see the inter-electrode gap at different points. This is the stagnation zone, this is the front zone, this is the transition zone, this is the side zone, Zone 1 is stagnation, that zone 2 is front, zone 3 is transition, and zone 4 is the side. So, this is the stagnation zone, this is the front zone, this is the transition zone, and this is the side zone. Anodic dissolution from side surfaces. Now, as I mentioned earlier, now if it is a completely bare tool, you can see this is the kind of the tapered workpiece you are going to get, and if it is a coated tool, then you are going to get a straight sides of the drilled hole. So, here it is partially coated and this is bare over there. Determine inter-electrode gap at different nodes by one of the methods or models, finite element model, boundary element method, and so on, and then join different inter-electrode gap nodes to predict the anode shape. Side gap machining with A uninsulated tool and B with insulated tool. This is insulated tool, this is uninsulated tool. Anode shape prediction methodology, numerical analysis approach. Use of high speed computers is required. Different steps are to be followed. Decide type of analysis you want, whether 1D, 2D or 3D. Collect initial data. Perform preliminary computation. Solve the finite element problem either as temperature distribution. This is very important because the problem can be solved in a different way. Here you are giving major emphasis on the temperature variation along the electrolyte flow. So, you can't solve the finite element with the help of the finite element method temperature distribution problem, and then with temperature distribution you can calculate the electrolyte conductivity at different nodes and then the inter-electrode gap. However, I have already mentioned that while doing so you should take the effect of void fraction and also you should take the effect of sludge formation, otherwise you will not get accurate results. Or you can, in place of temperature, you can use electric field potential distribution and then accordingly calculate the current density, and while calculating current density find out the, after calculating current density you can find out the material removal rate. Again here also you can take into account the temperature variation, otherwise your results are going to be weaker or not very accurate. Calculate secondary variables such as temperature distribution, electrolyte conductivity, current density, etc. at each node. Calculate the inter-electrode gap along the electrolyte flow direction for each node, and then finally using the computed inter-electrode gap at different points or nodes, make anode profile by joining them. And once you join these different points either in 1D, 2D or 3D, what you get is known as computed anode profile. Here goal is to determine the inter-electrode gap at different nodes on the workpiece. These nodes are due to the elements, and you can have different kind of elements, 1D element, 2D element, 3D element, depending upon which problem you are solving, 1D, 2D or 3D problem. And in say 2D also you have different shapes, rectangular shaped element, triangular shaped elements and so on. Temperature distribution in inter-electrode gap is appropriate differential equation to evaluate temperature distribution along the electrolyte flow direction. Differential equation can be solved by finite difference method, finite element method, boundary element method or some other technique. From the above temperature distribution, calculate electrolyte conductivity at different points, nodes on the elements as I have mentioned in earlier slide also. Find effective feed rate at different points due to the inclined anode surface. Now, this is very important. After first cycle, material has been removed from different points along different elements, and this will change the straightness of the workpiece, whether it is a flat workpiece or it is a hole, whatever it is. And once that straightness changes, then there will be different angle between the normal and the perpendicular to the workpiece surface. So, effective feed rate will change, and you should calculate at every node wherever you are calculating other parameters the effective feed rate, taking this into account. Assumptions: Ohm's law is followed, this is assumed, but in real sense it is not very true. Compute current density J at different points, assume J, that is current density, calculate the inter-electrode gap at different points or nodes along the electrolyte flow direction. And once you have done that, plot N shape from the inter-electrode gap at different points. As I mentioned earlier, join the inter-electrode points or nodes to get final anode profile. Important assumption: Ohm's law is obeyed, which is not true in real sense. Lines of electric field potential are not always straight and normal to the electrode surface. This is the assumption made while following Ohm's law, but which is especially when a curved surface is there, curved zone is analyzed, this is not true at all. So, that is the reason that our assumptions are not very accurate or are not realistic. That is why you get difference in the simulated anode profile and experimentally obtained anode profile. Hence, the solution of Laplace equation is recommended instead of Ohm's law. Laplace equation is recommended to be used for analyzing the anode shape prediction and tool design problems. Electric field potential distribution method. Calculate electric field potential by solving Laplace equation in 1 dimension, 2 dimension or 3 dimension. This is the Laplace equation in 3 dimension, del 2 phi over del x2 plus del 2 phi over del by 2 plus del 2 phi over del z2 is equal to 0. Now, here phi is equal to 0 at the cathode and phi is equal to EV, that is the effective voltage, and it is nothing but applied voltage minus over potential, and that is at the cathode. So, you must consider this as over potential, otherwise your results are not going to be accurate. Calculate current density at different nodes or points using this equation. Del T over del x is equal to V minus dV, that is over potential square, U0 rho E C E by 0 square is equal to A K. Here K is taken as A is taken as constant and K is the electrolyte conductivity. Now, here K is missing from this particular point. So, you can add K over here after this bracket. So, K is the electrolyte conductivity. Find temperature at different nodes, points and use it to modify electrolyte conductivity. Now, while modifying this electrolyte conductivity, I am mentioning it repeatedly, account for the change in temperature, void fraction and sludge formation at different nodes. Compute current density at different nodes, compute inter-electrode gap at different nodes or points and connect these inter-electrode gap points and predict the anode profile. Now, these steps are summed up over here. Simplified flow chart for anode shape prediction using finite element method. Start, read given data and print input data, generate nodal coordinates, generate stiffness matrix that is used in finite element method, compute number of computation cycles for how long you want to compute, or you want to computational machining, you want to do computational machining, that should be computed and it will be decided what is the maximum material at particular point you want to machine. Compute feed rate in different zones, this is very important. I have told you that workpiece surface does not remain straight or vertical, it becomes inclined. So, at different points feed rate will be different. So, accounting the cos theta or theta angle of inclination, you should calculate the feed rate. Apply boundary or initial conditions, solve the equations to evaluate potential temperature at nodes, compute change in electrolyte conductivity due to the change in the temperature, compute electrolyte conductivity. If feed rate is 0, yes, compute Y, that is inter-electrode gap for 0 feed rate. If no, then compute Y for finite feed rate. We have already seen it will be different for different feed rates, either 0 feed rate or finite feed rate. Then find current density, compute linear and volumetric material removal rate, reassign Y coordinates for the side flow, modify V, that is voltage, for new value of Y, print results and end. Now, please check here, check if machining cycles are complete. If not, go to step this one. If machining cycles are not complete, then you should go to the step shown over here in the earlier slide. So, that will help you, because you have to recalculate everything up to this point. You have to come up to this point by recalculation, and if it does not satisfy condition, then again you have to go back to the step where $$ is written, and once it is satisfied done, then you can stop. Now, there are various approaches for anode shape prediction. Let us see what are the various approaches. Approximate methods, but comparatively simple to use. Now, approximate methods are including numerical methods also. Empirical approach, exact path of electric current flow lines within a complex interelectrode gap is difficult to determine analytically, and once theoretical analysis is difficult, then one goes to empirical approach. Empirical equation suggested by Koenig and Paul to evaluate interelectrode gap A0 at the start of the transition zone is given here. A0 is equal to RC raised power 0.35 multiplied by 0.35 and 10 E star into by E. By E is the equilibrium gap, E is the Euler's constant and raised to power 0.5, where by E is the equilibrium gap greater than or equal to 0.5 millimeter, less than or equal to 0.6 millimeter, and RC, that is the corner radius, which is given over here, tool corner radius, that is greater than 0.5 millimeter and less than or equal to 5 millimeter. Now, where E is Euler constant or Euler number and RC is corner radius, by E is equilibrium gap. For the case of tools partially or fully coated on side wall, this was for bare tool, side wall and having RC greater than 1 less than 5 millimeter, RC, that is the tool corner radius, they have proposed this equation A0, because this is the different case. For the bare tool, this is for the partially or fully coated tool. This equation 0.1 plus YA into 0.314 RC plus 1.17. Why it is empirical? Because all these equations are based on experimental results, and they have analyzed these experimental results and determined these constant 0.314, 0.1 and so on. Here BB is the bare bit length, it is 0, and for YE equilibrium gap greater than or equal to 0.1 millimeter, less than or equal to 0.7 millimeter. A0 2 by E plus 0.1 6.283 into RC minus 1 whole raised to power 0.5. This is for BB, bare bit length greater than or equal to 1 millimeter. So, the constant they are depending upon what is the bare bit length of the tool, and I have already shown to you what is the bare bit length of the tool, and in case of bit type of the tool, whatever is the size of the bit, that is the bare bit length, because rest of the tool is made of electrically non-conducting material, that is perspex or some other material. Above equations are reported to yield erroneous results at low feed rate. Here feed rates are given. Here if feed rate is less than 0.006 millimeter per second and large equilibrium gap, if equilibrium gap is greater than 1 millimeter, then these equations do not give satisfactory results. Regression analysis of experimental data gauge is given by Jain and Pandey. This is the equation they have proposed. A0 is equal to RC1 minus YE plus RC2. RC1 and RC2 depend on many factors like tool and work material combination, electrolyte, etc. This is the very simple equation proposed based on the experimental results. Equations to evaluate interelectrode gap AS and AS dash in the side zones under coated and bare tool, bare part of the tool. Koenig and Paul, his group has proposed this equation. AS is 2 BB by E plus RC raised to power 0.7 multiplied by this constant into 10 E star into by E plus 0.65 by E. Here it is raised to power 0.5. And AS1, that is another part that is given over here, is equal to 2 BB into by E plus A0 square raised to power 0.5, that is under root. So, you can see here different equations are there based on experimental results. Nomographic approach. In fact, on the shop floor, people are not well educated and they cannot understand the usage of all these equations, etc. So, what people have done, they have proposed a nomographic approach where they have given a set of graphs. In these graphs, you just put the values of the bare bit length, tool corner radius, tool diameter and inter-electrode gap, and you will be able to predict the side gap at different locations. Nomogram for the determination of the side gap AS, this was proposed by Koenig and Paul long back in 1970. For the calculated AS and R, that is the corner radius, find point A, that is shown over here, line parallel to the x axis which cuts at point B, that is this line, and then for AG and BB, bare bit length, and AG is the that inter-electrode gap, find point C, that is the point C here, this is the inter-electrode gap, you are given the inter-electrode gap, and you are given the BB, this is the BB bare bit length. To calculate, find out, locate it and then find this point as like this, this is over there, that is the point C. Draw a line parallel from point C that cuts over here at D, and then to the x axis to cut at point T, and you cut this here also. Now, join D and B, this is D and this B. So, you join this to cut at E, this is point E, it is cutting at E. Now, find point F from inter-electrode gap, this is the inter-electrode gap, E, F from inter-electrode gap, and draw a vertical line, and from E, this is the E, draw a curve parallel to the plotted curve to cut vertical line at G. Now, these are the curved lines. So, from here you draw a line, curved line parallel to this line already drawn, and this will cut this vertical at point G. So, this point G gives the AS, that is the side gap. So, this is how people who are not highly educated and who cannot use these equations, they can find the side gap from these nomograms, and these nomograms have proved to be very helpful on the shop floor. And once you know the side gap or side inter-electrode gap, you can easily predict the anode profile. Now, this method, cos theta method, is applicable when angle theta between feed direction and normal to the workpiece surface or tool surface is gentle. This method was proposed by Tipton. It is not applicable in case of sharp corners. It is applied for three regions: theta is equal to 0, 90 degree, or theta some other angle in between. Now, inter-electrode gap is by E for theta is equal to 0, and inter-electrode gap is by E over cos theta for theta greater than 0, but less than 90 degree. This is very important equation, because as I mentioned in the earlier slides, you have to calculate the feed rate at different locations, because inter-electrode gap is also going to change accordingly. Inter-electrode gap is parabolic in shape if theta is equal to 90 degree. Cos theta theory is not applicable to regions. Now, they are shown in the figure. Assumption: current flow lines are straight, parallel and normal to the tool, workpiece or both surfaces. Tool and workpiece surface, they are uniform in z direction, that means basically they are considered in 2D. Let workpiece surface be y is equal to the function of x. Point A on workpiece transforms to point B x1 by 1 on tool y over cos theta from workpiece surface. You can see here these are the three. This is the theta is equal to 0. So, you have interelectrode gap equal to by E, theta is equal to 90 degree over here, this is vertical, and feed rate is also in this, feed is also in this direction, and this is cos theta in between the two. Here it is normal to the cathode, and this is the workpiece surface, and you can see here this is the interelectrode gap which is by E over cos theta. You can see here cathode design by the cos theta method. You can transform the workpiece surface A surface here point A to the point B. How to do it? We will discuss it later on. So, if you have this as the tool point, then you can get this on the workpiece surface, and that is what we are interested in, that comes under what is known as cathode design problem, and this is the used for anode shape prediction as well as cathode design purposes. Y minus y1, that is the gap at any point 1, that is AV cos theta we have seen there, and that is by E over cos theta into cos theta, that becomes by E, equilibrium gap. Now, you can see here this is the theta, right, different, this is the theta, this is x and this is y, and here those are the same point A and point B, theta is there, cathode is there, anode is here. So, x1 minus x, AV sin theta, AV is given over here, this is A and this is B, and AV sin theta it becomes x1 minus x, and that is by AV is equal to nothing but by E over cos theta, that is the interelectrode gap, and into sin theta. So, this becomes by E tan theta. So, dy over dx is equal to tan theta. So, you get y is equal to by 1 plus by E from 1, that is equation this one, and you get x1 is equal to x plus by E dy over dx, because you can see here x1 is equal to x, if this goes on this side, then you get x plus by E tan theta, and this is x plus by E tan theta can be written as dy over dx, and y is function of f(x) that we have already defined. So, this gives you y e plus y1 is equal to f x1 minus y e dy over dx. Case 1 of cos theta method. Suppose workpiece surface can be approximated by a series of parabolic arcs, and this is the equation for parabolic arcs, y is equal to a plus bx plus cx square. From equations 4a and 4b that we are shown in the earlier slide, you can get y1 plus ye is equal to y, and y we are defining like this. So, substitute the values from 6b and 4b in 6a, this and this one equation. So, we can get y1 plus ye, that is this, is equal to y is equal to a plus b, and x we are defining like this in the earlier slide, x1 minus ye dy over dx plus c x square. So, square of this is like this. So, you simplify this, a plus bx1 minus ye dy over dx plus c x1 square, that is here you open this, square this equation, you will get c x1 square minus 2c by e x1 dy over dx and plus by e square dy over dx square, and we know dy over dx is a very small quantity. Now, differentiate equation 6a with respect to x, then one gets dy over dx is equal to b plus 2cx. You differentiate this equation, you will get this particular equation, and dy over dx is equal to b plus 2cx. Substitute the value of x from equation 4b that was shown in the earlier slide. So, you get b plus 2c here substitute the value x. So, x1 minus by e dy over dx. Simplify this equation to get dy over dx, that is this one, b plus 2c x1 over 1 plus 2c by e. So, you simplify this equation to get this particular equation. Substitute equation 8 in equation 7 and neglect small terms like ye dy over dx, because dy over dx and by e is already small, this is still smaller and square of this become further smaller. So, you can neglect these terms. So, what you get is y1 is equal to a plus b x1 plus c x1 square minus by e. This is the parabolic equation, by is a plus b x1 plus c x1 square minus by e is the equilibrium gap. So, workpiece is displaced by e, that is the equilibrium gap, and minus by e into b plus 2c x1 square divided by 1 plus 2c by e, and this is the known as the correction factor, and this is known as the workpiece displaced by e. So, you can predict the inter-electrode gap using this. Now, in cos theta method for case 2, this was for 0 feed rate, mind please note it, and this cos theta method is for finite feed rate. Workpiece surface represented by a straight line, y equal to a plus c, sorry, this is for a straight line case, not finite feed rate. This is for a straight line. To get tool shape, substitute c is equal to 0 in the above equation. So, this become a straight line equation. So, you get y1 is equal to a plus b x1 minus by e b square. From this equation you can get a plus b x1 minus by e 1 plus b square. You simplify this equation, you get this equation. Since y is equal to a plus bx, b is equal to tan theta, or 1 plus b square is equal to 1 plus tan square theta. So, you can use this. So, you can simplify tan theta equal to sin theta over cos theta, you get cos square theta plus sin square theta divided by cos square theta. So, you get 1 over cos square theta. So, here this equation can be simplified as y1 is equal to a plus b x1 minus by e over cos square theta. 3-dimensional analysis can also be done using x, y, z coordinates are given. Y is equal to function of x, z, it accounts for changes in z direction also. So, the equation becomes y is equal to a plus bx plus cx square plus dz plus ez square and so on. Second order equation for 3D. Following the above procedure, the tool shape can be represented by y is equal to a plus bx1 plus cx1 square d plus dz1 square ez plus ez1 square plus gx1 z1 minus ye, that is the equilibrium gap, minus by e this much. So, this is the correction and this is the displacement of the surface by e. So, this is the workpiece surface displaced by e over here, and this is the correction for the gradient of the surface, this whole part. So, this is how you can even find out for the 3D surfaces. So, what we have done in this lecture: introduction to tooling design for ECM and ECMM, anode shape prediction in ECM and ECMM, various methods including cos theta method, numerical approach including finite element method, finite difference method, complex variable approach, nomographic approach, etc. And I have already mentioned the nomographic approach is very useful on the shop floor. However, to get the better results and accurate results, you should go for finite element method. In some cases, one can use finite difference method, but more accurate is finite element method. And then tooling design methods including cos theta method, complex variable approach, finite element method, finite difference method, correction factor method, etc. Although I have not discussed correction factor method, but this is most recent and very useful for tool design purposes. So, we will discuss it in the next lecture. Now, flowchart for anode shape prediction have been given in this lecture. They can be exhaustive also, and it is used in numerical methods and analysis of some of the methods. Other approaches for anode shape prediction in ECM and ECMM, some of them have been discussed in this particular lecture, but all of them have not been done because otherwise it becomes too long. So, you can find them from the different research papers and from the book. Now, in the next lecture, we are going to discuss about the tool design problem, how to solve the cathode design or tooling design problem. Thank you very much.